Good afternoon. The time is now 12:04 and the webinar will begin. Welcome to the OPWA Education Series webinar on cast iron pipes in the water distribution system, making informed decisions on renewal plans. I'd like to recognize the sponsors of OPWA who help make events like this possible. Thank you for your support. For today's session, your microphones have been muted and your cameras have been turned off. If you have any questions, please click on the Q&A icon at the bottom of your screen and Rabia will address them at the end of the session. So thanks again for joining us today. My name is Max Ross. I'm on the board of directors for the OPWA. OPWA is a not-for-profit organization of professional public works practitioners. We are the Ontario chapter, the Canadian Public Works Association, and one of 55 chapters of the American Public Works Association. We have over 600 public works practitioners employed in provincial governments, municipalities, consulting engineering firms, utility companies, contractors, and suppliers. The chapter is also set up into geographical areas with two branches in the Niagara region. There is the West Central branch, and in the Ottawa region, there's the Ottawa Valley branch. For the non-members joining us today, welcome, and I ask that you give consideration to joining OPWA. So this OPWA Connects event is in alignment with our mission statement, connecting public works community. The Ontario Public Works Connects is a new program intended to help OPWA membership connect to educational and technical resources, as well as to other members. Webinars are one example of providing those resources, and our aim is to host a new webinar each month. To learn more about the chapter, its upcoming events, and the resources available to our members, please visit opwa.cpwa.net. If you're looking to get more involved in the public works community, we would also encourage you to consider volunteering for one of our many committees. And with that, I'll introduce our speaker, Rabia Maddy. Rabia is the manager of Pipeline Condition Assessment and Rehabilitation at CIMA Plus. He's a registered professional engineer in Ontario, BC, and Nova Scotia, in addition to a certified NASSCO and PACP, MACP, and LACP, with over 20 years of linear infrastructure experience. Rabia has extensive experience in planning, implementing, leading field staff, and managing pipeline and manhole condition assessment projects for water and wastewater linear infrastructure projects, and interpreting inspection results into asset management frameworks using advanced reliability and engineering analysis methods. Furthermore, Mr. Maddy has hands-on experience working with a variety of technologies, including working with different pipe materials such as cast and ductile iron pipes, concrete pressure pipes, asbestos cement pipes, and PVC pipes. Rabia is the author of several papers and articles on managing cast iron pipelines, and he is a member of the AWWA M77 committee. Mr. Matty knows asset management, pipeline and manhole condition assessment, asset management, advanced statistics, engineering, operation, CIPP rehabilitation designing, project management methodology, and he also provides quality assurance reviews for water and wastewater linear infrastructure assessment reports. So with that, I'm going to hand things over to Rabbi Matty.
Thank you, Max. Thank you for the introduction. Hello, everyone. It's a pleasure to be here with the OPWA. Today, we're going to talk about the cast iron pipes in the water distribution system and how we can leverage the understanding of assessment of these pipes to make a more informed decision on how to manage these pipes and or renew these pipes. I prepared for today an agenda. So we will be talking about, we're going to have an introduction. I thank you, Max already did that. I always like to start every webinar with the safety minutes. We're going to talk about how to establish a cast iron reliability analysis framework. We're going to talk about what inspection tool to use, because there are lots of technologies out there in the market. And the question is, what's the best tool to use? We're going to talk about the distress status of a cast iron pipe, how we can describe a distress status of a cast iron pipe. We're going to convert the assessment findings into an asset management package that helps us utilize the inspection findings into an asset management enterprise system. We're going to also use the unleveraged inspection findings and have a pipeline renewal plan that correlates with the AWWA M28 manual in having a decision-making tree. And of course, we always have room for questions and answers. With this agenda, I will start talking in the introduction. So Max already provided the introduction. So this is just a brief introduction. I started doing 8 years as a regular designer, doing water distribution mains, feeder mains, sewer collection system as a designer. Then I moved into the public sector for 6 years, from a project manager to the director of the infrastructure system. This is where I started doing my first condition assessment projects. Then I moved into the technology vendor sector. I worked for 3 years with a technology vendor assessing pipelines. Then I moved back to the condition assessment sector with a private company for another 3 years. And now I am with SEMA. And I'm also a member of the AWWA M77, the North American Watermain Condition Assessment Committee. Safety minutes, since I think everyone is working from home, so I thought it will be a very interesting slide to share with everyone. So everyone's sitting on their chairs. Just don't forget that we need to do a desktop stretches. It's always beneficial to do these stretches, walk around the house or outside if the weather allows it, just to prevent any neck, shoulders, or stiffness or any type of that pain. Very recommended. So to start, why to establish a cast iron reliability analysis framework? The classic approach, we have the asset inventory, and in this case, since we're talking about the cast iron, we locate what types of asset do we have. We prioritize these assets. We understand what's the distress indicator of this asset. In this case, for cast iron, is the remaining wall thickness. And then we will have a desktop assessment approach or a physical assessment approach using direct measurements. And then we can get the remaining wall thickness, the residual remaining wall thickness, if we're talking for a cast iron. And it will be a specific oriented projects. And once we collect more and more data, this is where we stop. So we always say, okay, what's next and how we address these things. So the more innovative approach is looking at condition assessment as part of an entire structure that a pipe owner or a municipality owns. So if we look at the condition assessment of part of an asset management perspective, so in general, every pipe owner through asset management or different type of groups such as program management needs to make sure that they're operating their system safely on a 24/7 base, and they have to make sure the system is reliable. And the way they measure reliability is by the level of service. Now, there are different types of how to measure level of service. One of the way when we talk about linear infrastructure, we measure the level of service by the anticipated service life of this pipe. This anticipated service life is a design anticipated service life that we get from the manufacturer. And if in the case of cast iron, looking at different research out there in the market, the anticipated service life that they discuss is 75 years. And this is where the condition assessment program comes into handy. And the addition condition assessment program can identify the gaps between the desired level, and in this case, the anticipated service life, and the actual state condition, which we can identify using the condition assessment or inspection tools. The gaps between the desired level and the actual levels can be bridged by a capital program that we can develop, and that's where the renewal and versus replacement or rehabilitation. Other pipe owners also leverage the inspection findings into an asset value assessment when they do the appraisals, or and when they want to take their asset for depreciation and they want to value their asset values. So they use the estimated service life based on an actual state condition instead of using the anticipated service life, and therefore they can assess the value of their asset more properly rather than just take the anticipated service life, which, by the way, assumes that the pipe came from the manufacturer without any surrounding environment impacting of the pipe. Looking at condition assessment more as a part of an entire asset management framework is more proper way to going down the road to look at it. And instead of talking about individual projects, we're going to start talking about programs that are utilized to identify the gaps between the desired levels and the actual state conditions. I always been asked what the most proper inspection tool to use. Before we select the inspection tools, we need to prioritize the pipes for assessment, starting from identifying the failure modes from structure to hydraulic to quality. Because we're talking about failure, so we're going to focus more on the structural failure mode. Since we're talking about cast iron, the distress indicator is corrosion, and therefore we need to select technologies that can identify the residual thickness of that pipe. And we will prioritize these pipes based on a risk-based approach that takes into consideration the consequence of failure and the likelihood of failure. Now, the likelihood of failure that we are considering at the beginning, it's a desktop assessment tool. It's the initial likelihood of failure, and it could be on several existing models out there in the market. For example, based on breakage history, all the Weiber distribution models, if you have sufficient data. If you don't have sufficient data, you can base it on strength reduction models. One of the papers that I wrote is on the strength reduction models for clients that do not have sufficient breakage history, or use an empirical models such as Belvant model or power models or any empirical model out there in the market that you can utilize. The multiplication of the consequence and the likelihood can provide us pipes and prioritizing pipes for assessment. Once we identify these pipes of concerns, we need to select the inspection tools. And as when we remind everyone, the distress indicator, we need tools that can identify the remaining wall thickness of cast iron. The traditional way, or many other clients use, they have a selection matrix. And this matrix goes talk about the pipe links coverage, how much inspection coverage we can do, and they talk about the inspection accuracy. So basically they have two components in general, the inspection links coverage and the inspection accuracy and a program level. And based on the scoring of each technology and the matrix that we're providing here, they will select the inspection tool. It's a straightforward method, but the problem with this method is it doesn't take into consideration other factors and other criteria that the pipe owner may have, and in particular, for example, the operation team, because the operation team, since they are the ones who are very integrated part of the inspection itself, they should have a say into what the best tool to use in order to have this assessment done. Therefore, we advance the studies in order to locate what's the best inspection tool to use by developing an optimal inspection tool. And the way to do it is we take all the technologies out there in the market, all the existing platform out there in the market that suit to inspect cast iron pipes, and we developed with the pipe owner an evaluation criteria. Samples of such an evaluation criteria, for example, inspection risks, enabling works requirement, the condition of branches during inspection, water quality risk, accuracy of defects, in-service in tools versus outer service and tool, and so on. Each client has its own needs, and usually we bring these evaluation criteria based on different groups within the client: the program management group, the asset management group, the operation and maintenance group, and the engineering group, and so on. Examples of, for example, how we identify inspection risk is the way we identify this group or this criteria is by identify is the effort associated in to retrieve a tool that got stuck in the system. And that effort can be vary from no risk because the tool is external into excavation and cut in order to retrieve that tool. Once we develop this criteria with the client or the pipe owner, we start to develop the weights for each criteria. And we use a straightforward statistical way, which is called the pairwise approach. So we collect the input from different departments, again, different departments, engineering, operation, and based on these weights and the criteria that we develop, we can select the most optimal inspection tool that can suit the client needs based on the criteria we developed. So it doesn't have to be the most accurate. It doesn't have to be the most tool that covers everything. It's the optimal tool that can suit the needs for the client and can answer the goals and objective of each task. Based on that, we can select the best, highest scored tools that can help the client do inspection and build inspection budgets accordingly. Some samples of tools relevant to do remaining wall thickness. One of the main thing here is to say there are tools that can inspect localized, and there are tools who can inspect segments. Since we are talking more on a program level, hence pitting depth measurements will be excluded, and any types of tools that does localized inspection and usually on an exposed pipe will also be excluded, such as radiographic and CT scans. However, we have several tools out there in the market, starting from electromagnetic principles, wave propagation principles, ultrasonic tools, and we have on the right different types of tools. For example, the PCAT, it's a wave propagation tool that uses transits into assessing the tool by converting the velocity of the wave from point A to point B into the remaining thickness. We have sonars, we have pipe scans, we have acoustic measurements. We have a tool called the Sea Snake that Pika used. The ePulse belongs to Ecologics. The pipe scans belongs to JG7. The sonar belongs to Kenwave. The PCAT belongs to Detection Services. The different EM principle and so on. Very important to identify that the tools on top are tools to measure remaining wall thickness. However, there are other tools in the market that also can inspect leak detection. The difference between remaining wall thickness and the leak detection tools is an absolute result that tells you the pipe has a leak or doesn't have a leak. And there are different types of platform, from Swiss swimming platform like the SmartPod that Pure owned, to tethered tools like with a cable like the Sahara or the JD7 that they own, or the correlators out there in the market. So this is just a general spectrum of the available technologies out there in the market. Utilizing the concept of an optimal inspection tool, the client or the pipe owner will select the top 3 tools that they prefer to use, giving the criteria that they developed based on their goals and objective. And based on these tools, they can start building their condition assessment program. Again, because we're all working at home, it's very recommended that everyone has its own stretches just to make sure we will keep our neck and shoulders in a very good shape. Understanding cast iron distress status. So in the end of the day, these inspection tools provides you the remaining wall thickness. So the answer is, what are we going to do with that? Okay, I have a pipe of 20% wall loss. I have another pipe by 15% wall loss. What does it mean? What it will help me? Now, in order to describe cast iron distress status, one way it was way time followed, some client owners still follow it, is by based on number of defects occurrence, which basically they have a breakage history, and based on the number of occurrence of defects or breaks, they will provide a rating from 1 to 5, and based on that rating, they will decide to replace the pipe or not. For example, if a pipe failed a specific segment. And when we see segment, it's a pipe links between one node to another node. And in general, in North America, it's around 150 to 200 meters. And they say if this pipe breaks 4 times, then it will have a condition grading number 5. And based on that, I will decide to replace this pipe. In the end of the day, how we are describing the distress status or our condition grading system is basically we wait till the pipe till fails. So it's fix it when it breaks. Obviously, we want to take more a proactive approach rather than reactive approach. And one of the greatest samples out there in the market is the NASSCO concept. NASSCO has a straightforward way that it's a systematic, constant, and uniform way how to rate pipes, and it gives you a rating between 1 to 5. And based on this rating, you do the inspection, you can correlate the inspection results into a condition grading or a rating system that everyone uses the same thing. And based on that, they will make sound decisions, and you can computerize this approach in an asset enterprise system, which is a great thing because it's constant and uniform. However, the question is, can we take the same terminology that is being employed in NASSCO for gravity pipes into cast iron pipes? Now, one of the most important things when we talk about NASSCO, NASSCO uses the inspection findings output only in order to provide you the condition grading as we saw in the scoring matrix that in the previous slide. However, for pressurized water main, the story is different. And the inspection finding or the physical condition does not give you the entire picture. And why? If we look at cast iron pipe, it's a rigid pipe material. And the way rigid pipe material is designed, it depends on the strengths to resist the loads acting on it. Therefore, when this pipe, in order to fail, it needs two things. It needs that the pipe will deteriorate with time, or with the time of exposure to aggressive environment, and the acting load on it needs to operate to a point that it will overcome its ability to resist the loads, which in other words, failure to happen is inability of the pipe material to resist the loads acting on it. And in the graph that we're seeing here, we are seeing that the pipe strength is deteriorating with time. It doesn't have to be linear. It could be a different concept how it behaves. It's based how we assess the deterioration rate of that pipe. And we have the fluctuating stress, as we see here, acting on the pipe wall. Once the residual strings cannot resist the stresses acting on it, this is where we're going to anticipate failure. And to boot on that, and that's in the next slide, this is an actual physical inspection that we did. We inspected two pipelines, cast iron, 12-inch, same thing. One pipe is installed from 1919. The other pipe was installed in 1921. So they're pretty at the same age. They're only 250 meters separate. And the inspection results came back. The pipe on the right side is 20% wall loss, and the pipe on the left side is 20% wall loss. From just looking at it and just looking at a general classification matrix, we will come and say, okay, if we assess that the pipe between 10% and 30% is in a moderate way, okay, we will assess that this is a moderate condition of this pipe, and based only on remaining wall thickness. However, the truth is the pipe on the right side on Commissioner Street failed 4 times. However, the pipe on the left side never failed. It's over 100 years old and the pipe never failed. That proves one important fact. For a failure to occur, we need two things: not only the physical condition of the pipe, which we detect through an inspection, but also the applied load acting on the pipe. And combining the two things together, then we can understand when or predict when the pipe will fail. And we can also describe the distress status of that pipe. By the way, the pipe on the right, when it failed the last time, that actually well, there was a big sinkhole, and there's a TTC car that went inside in that sinkhole, and it was all around the 6 o'clock news. Understanding this terminology, the wall thickness or the technology what provides only remaining wall thickness is not the entire picture. Therefore, combining the imposed loads and the wall thickness together, this is where we understand what's happening with the pipe. The relationship between the wall thickness and the loads is defined in the design standards for the specific pipe material. Belvant in 2000, he was the first to talk about this concept, and he used something called the residual factor of safety methodology, which is something very similar to what we're talking here, is by instead of saying that the residual factor safety will start to decrease with time based on the loads acting and the physical condition was exposed to the aggressive environment. And therefore, the pipe will lose of its strength to a point that he cannot resist any more of the loads acting on it, and therefore we will have a failure. So how we take the cast iron pipe using different types of technologies to inspect the cast iron pipe in order to build a mechanism to describe this distress status. And this is a way that we are proposing. We take the inspection finding, in this case, the remaining wall thickness, and we translate the inspection finding into address distress status in terms of condition grading of 1 to 5. And this type of language that basically the system can understand, following the same terminology of NASSCO terminology. And this, what happened here is we took the design standards, because the relation between the physical condition and the acting load is the design standard, and we developed something called the non-dimensional condition grading curves. And you have several curves. Each curve represent a residual factor of safety. And based on that, we will understand based on the acting load on the pipe. And in this case, in the x-axis, you have the loads representative of internal pressures. And you have on the y-axis is basically the vertical loads acting on the pipe. And the dot inside that graph is basically the condition assessment that we got from the inspection. And based on the different inspections, now when we inspect a pipe, we don't say only, oh, the pipe has 20% wall loss, but we translate the information into a distress status in terms of a condition grading. And now we understand, for example, condition grading 1, the pipe is in a good condition, and even with the whatever it's been deteriorated, the pipe is still in good condition. Once it passed condition 1, then the pipe started to deteriorate. In the sample we are providing, that's point A. So point A, based on the acting loads, internal pressure and vertical loads, and the inspection findings, we assess that the pipe is now in condition grading 2, which means that the pipe passed its good condition and now it's starting to deteriorate. One of the good things about the non-dimensional curve, it's basically we can also assess the inspection frequency, using a deterioration model based on, it could be an empirical, it could be any statistical model, anything the client owner likes to use. We can now assess when the pipe will move from condition grading 2 to condition grading 3. And if the pipe requires to move from condition grading 2 to condition grading 3 uh, up to 5 to 7 years, then we can plan the next inspection more properly and justify the returning and inspecting that pipe in order to see if the pipe is behaving according to what we estimated. Therefore, translating the inspection findings into a distress status in terms of condition grading allows pipe owners to make more sound decisions and convert their inspection findings into a language they can understand better. And speaking of a language, one of the main issues that asset management use is the remaining service life, because they want to compare that into the anticipated service life and accordingly make sound decisions. One important fact, so we can use the inspection findings to calibrate existing deterioration curves that the client may have. That could be based on an empirical model or a statistical model or whatsoever. And then the sample of the graph on the left, we have a model. In this case, we use the an empirical model in this case. In this case, we use the Belvan model that was proposed in the year 2000 for cast iron deterioration, because the Canadian National Water Research did a lot of research on cast iron. So what we actually did is, because in this model, they're offering a range of parameters to use, we calibrated this model using an actual inspection results, and therefore we calibrated the parameter into better, and now we have a more representative deterioration curve. One important fact when we do the remaining service life is there's always uncertainties. The uncertainty starts with the technology itself. There's no technology can give you accurate results. And there's also the original thickness of the pipe. Also, it vary along the pipe. When it comes from the manufacturers, there's always plus minus 3% of the initial thickness of the wall that it's vary. Also, the in surrounding environment also has lots of uncertainties, and it's different from one location to another. Therefore, giving these uncertainties, the assessment itself will exhibit uncertainties also, and therefore we need to address it. And the way we address it, we use a straightforward way. It's Monte Carlo simulation in this case. And we develop something called the survivor curve. And based on the survivor curve, it's the accumulative probability and the term of year. And we have here the graphs that we see here on the right side. Now we have two graphs. One of them represent two, and these two graphs represent two different pressures. Some clients says I want to represent the pipe based on the pressure rating only, because this is why how I bought this pipe out of the shelf, that this pipe was designed to resist the internal pressure rating. And once this pipe cannot resist anymore the internal pressure rating, I need to adjust my system. Other people believe that we should assess these things based on the operating pressure plus the surge allowness. And based on that, we will detect how much the pipe will survive. Giving the load acting on the pipe from vertical and internal pressure, depending on how the client see it, from a pressure rating or the operating pressure plus the surge, we can develop the surviving curve and estimate the remaining service life and have the probability, accumulative probability, how much the cumulative probability will have it. Some clients believe that the level of service is 90%. Once the pipe hits 90% accumulative probability, this is where they will dictate what is the remaining service life. And as I said, there are some other pipe owners took the inspection findings from the remaining wall thickness, converted into condition grading using the non-dimensional curve, and taking that assessment into a remaining service life. One of the additional values that the condition assessment can provide you is when they do an appraisal for the asset value. And for example, in this case, from the literature, we know cast iron is a 75 years old. So if we have a sample, in our specific sample, we have a cast iron pipe installed in 1956, based on the manufacturer or the literature or the adopted anticipated service life when they designed that pipe, assuming it's 75 years, then we anticipate that this pipe will survive to 2031. And based on that, they will do the asset depreciation, and they will come out with in the appraisal that will give you the asset value. However, now we know that in order for a pipe to fail, the physical condition is not the entire picture, but it's also the acting loads on the pipe. Taking that into consideration, we will see that if we assume that the pipe, and in this case, the orange pipe is geared towards the pressure rating, and if we have a pipe, the remaining service life is base is 2046 up to 2054. and that is geared for operating pressure or pressure rating, depending on how the client sees things. And now we have a different value that we are using in order to assess the asset value, which means when we do the asset depreciation in the appraisal, the asset has more value than just looking at it from an anticipated design life that we started taking or took it from literature. And if we were working in a higher pressure, obviously the pipe will have a lower remaining service life because the loads acting on the pipe is different. Obviously, if we have a pipe with a more aggressive environment, it will survive less. Therefore, we can also not only leverage the inspection findings to make sound decisions into what to do, but also assessing the asset value in a more proper way. So we're taking all our inspection findings using wall thickness measurement, using a correlator inspection tool based on acoustic technology, or using an EM principle, different tool depending on the optimal tool that the pipe owner selected, doing soil analysis, water analysis, C-factor testing, and leak detection and transit pressure monitoring. This is the field measurement that we recommend. Out of these field measurements, as we saw, we can give the pipe a condition grading. And with the condition grading, we have a proposed decision-making tree and how to do it. So if the pipe gets a condition grading 1 or 2, which means that the pipe is in a good and fair condition, we always recommend to do additional soil sampling to see if we have too much aggressive soils. And if we have more aggressive soils, then it will be recommended to do more frequent inspections in order to keep an eye on that pipe. If we get the condition grading of 3 or 2 to 3, then we recommend to do leak detection. Now, yes, there are some tools that has added value that in the same inspection runs, they can do remaining wall thickness and leak detection in the same inspection run. For example, the correlators based on acoustic technology. Other inspection tools, they will need 2 separate tools in order to do a leak detection separate, and they will do after that the remaining wall thickness. If we do an assessment and we found a leak, we don't found a leak, then we I always recommend to do a C-factor assessment. What does the C-factor provide us? It provides us the internal condition of the pipe. If the C-factor is low, then we ask ourselves, it means that it has a lot of turboculations inside the pipe. Then we ask ourselves, do we need to upgrade that size? If the answer is no, then we go with a class 1 rehab. And what is class 1 rehab? Is basically relining an internal coating inside the pipe to make the pipe more smoother and to improve the hydraulic performance. If the pipe needs to be upgraded in the pipe size, then we will go and replace the pipe because we already know that we need to upgrade that pipe. If the C factor came back in a good condition, then we test the water, and based on the water sampling, we will decide what to go. If we have and given the fact that we're talking about potable water, usually the water sampling comes back with a good condition. If we found out there is a leak in the pipe, we should ask ourselves if it's a point leak. If it's a point leak, therefore we will fix that locally, and then we will do an assessment of the C factor again in order to assess the turboculation of that pipe, in order to see if we need to improve hydraulically the pipe by improving the C factor, or we need to upgrade it down the road. If there's multiple leaks, then the path is going to, again, we ask ourselves if we want to upgrade it, if we replace it, or we want to rehabilitate it. Now, one important thing to talk about here is there are some technology vendor are leveraging the wave propagation or the acoustic signal also to give you the extent of the C factor or the tuberculation. And these are advancements that the technology vendors are offering instead of the client doing C factors on its own. If we get a structure condition grading, which is high, 4 to 5, and in this case, as we saw in the non-dimensional curve, that it means that the pipe, the remaining residual factor of safety is reducing more and more and more, then this pipes needs to be intervened and we need to take an action. Now, the action, it will be compared between replacement and rehabilitation. If the pipe needs to be rehabilitated, then it's obviously we need to replace the pipe. However, if the pipe, to decide if we need to rehab or not, we have to build a criteria to assess. And the criteria can be, for example, how many connections we have. Is it an easy excavation or restoration? Is it a low consequence of failure? How much cost to do the cleaning? And based on the answer for these particular questions, and of course, each client can develop its own criteria, similar to we developed a criteria for selecting the most optimal inspection tool. We can also develop a criteria model, again, using the pairwise approach to put the weights on these criteria and select a replacement versus rehab. And based on the answer, if we are upgrading the size, then it's a replacement. However, if we're not upgrading the size, then we have to select between rehab or replacement. Based on the criteria we develop, and in this case, number of connections and everything, if the answer is yes, we're good, then there are too many connections, there are too many, it's not cost effective to rehab, then we will go with the path of replacement. And the constructability and visibility analysis shows everything that it's better to replace, then we replace. If the answer is no, then we will go to a class 4 or class 3 rehab. And it all depends on the hose pipe condition. If the hose pipe is in a very poor condition, then we will go on a fully structured rehab. And sometimes clients use the remaining wall thickness and they will, sorry, the remaining service life, and they will say, if the pipe is only didn't pass the 50% of remaining service, then they will go with a class 3 rehab. However, the selection between class 3 and class 4 is more driven by the cost. And since the cost of do the classes is more very close, therefore more and more clients are driven by only class 4. And this is a matrix how to take leveraging inspection findings into a condition matrix that takes into account the physical condition and the imposed loads acting on it using the relationship defined in the standards. And you leveraging this data into a decision-making tree. By the way, this can also be correlated to ductile iron and other pipe materials, including asbestos cement and different types of materials. Thank you for listening. I'm open for questions if there's any.
Well, thank you very much. A lot of really good information here. We have a number of questions, and maybe we'll start with what might be the easy ones first. Several people have asked if it's possible to get a copy of the presentation.
Definitely, yes. I will send it to you guys and you can distribute it for everyone.
Oh, okay, so OPWA will make that information available on our website. Okay, next question. Do you have a condition rating system for water?
For what?
For water, that is the question.
For Watermains, the question?
I presume that's it.
Yes. For the condition grading system, the same concept of having the physical condition, which we detect from a technology, and the applied load on it, the difference between the different scoring mechanism will be based on the pipe material, because each pipe material will fail differently. And I can talk, for example, on ductile iron versus cast iron. Cast iron is a rigid material. Therefore, its mechanism, how it fails, it's different from a ductile iron because ductile iron is more a flexible material. And as we said, the relationship between the applied load and the physical condition is defined in the AWA standards. And the standards for flexible materials is different from the standards that have been for rigid pipes. Leveraging these standards, we will develop the scoring mechanism that correlates to the pipe material, performance and behavior, and the way it fails. So each pipe material will have its own unique scoring mechanism that correlates to this pipe material specific failure.
Okay.
The
Great.
one we presented is for cast iron.
Okay. Next question then. What is the service lifespan of cast iron water main pipe? A range of 50 to 100 years is shown in one of the tables in your presentation. Why is this big range? Can you be specific on this?
Yes, so as we know, if we go back to the technology of cast iron, there were two main types, the spun and the cast, when they developed it. The early cast iron pipes in the 20s, they were developed without any lining. After that, they moved into lining these pipes. The problem with cast iron is when they were first developed, they were very thick pipes. However, they wanted with time to start to compete more and more and more, and they started to reduce the thickness of that pipe with time. If we go and look at the how much they, if you look at the technology over the history, they actually reduced almost from 50 to 60% of the original thickness from the 20s when they developed the first cast iron in order to be more and more competitive. Therefore, as we know, as more as they are reducing that thickness of that cast iron pipe, obviously the pipe will perform and behave differently with different types of loads. Therefore, the range for cast iron is we have this big range. However, this big range is based on how the literature looks at it. In our presentation, we prefer to give the anticipated service life, which based on actual inspection findings combined with the actual loads acting on it, which means if we have a pipe, even if it's distressed, but we're having a low pressure acting on it, the pipe will continue to survive. And one of the samples I showed in that specific pipe with the 200 meters separate, we have 100 years old pipe, and the pipe on the left, it will still survive for another 20 years and nothing will happen to it. However, the pipe on the right side, because in this case it's on a major road with high traffic volume and there's lots of settlements in the ground, which means there are lots of vertical loads from traffic acting on the pipe will fare more frequency compared to the pipe which is sitting in the middle of nowhere and there's almost no pressure acting on it and it's low pressures only. But for the question is why that difference? Because the technology of cast iron reduced its thickness starting from the 20s to the 60s, and it's almost half of its thickness it's lost to be more competitive.
Okay, all right. Last question then. Do you have some research findings for the effectiveness of cathodic protection on cast iron pipes? How long how long is the service life of cast iron pipe? Sorry, let me try that one again. How long the service life of cast iron pipes can be extended after cathodic protection?
So when we look at cathodic protection, I always like to say cathodic protection is a temporary solution in for a client that does not have the budget required to do renewal. When I say renewal, it could be replace, it could be rehab, it could be repair. That's the only reason when I recommend for a client to use the cathodic protection. Yes, it will increase the lifespan of that pipe, but keep in mind, cathodic protection will, when we add cathodic protection, it will stop the continuous deterioration of the pipe, but the pipe is already deteriorated. So if it deteriorated 25%, when we put that cathodic protection, it will stop the continuous deterioration, but it will not fix the pipe. Again, as we defined, that failure is a combination of not only the stress status of the pipe, but also the loads acting, which means we may have a condition that the pipe, we recommended a cathodic protection and the pipe was 20%, for example, wall loss, and we added the cathodic protection. However, there's a transit event that happen or a frequent transit events that happen, or there's settlements in the ground and trucks are passing all the time, and these loads are acting on that pipe and we had a failure, and then the pipe cannot resist with its existing strengths, cannot resist these stresses, and it will fail. Then the client will come and say, but I did cathodic protection. So the cathodic protection only serve as a stopper to continuous deteriorate of this pipe. And I always recommend it as a temporary solution for that pipe, because we also need to look at the loads acting. For the question is how long cathodic protection works, there are different research out there in the market. If I combine the average of them, it's between 5 to 7 years. It will give that little bit additional in between solution. But beyond that, I don't believe there you can actually implement it. And given the fact that the technologies out there in the market to replace and or rehab water mains, they are more accessible, are more advanced, the solution of doing cathodic protection becomes less desirable. However, it's still on the table as a temporary solution. This is what we recommend, because of the story that there may be loads acting on the pipe that leads for a failure.
Okay, it's great. So we have a couple more questions that have just come in. How do you incorporate transient pressure monitoring into cast iron asset management?
So when we have the non-dimensional curve, this is based on the design standard, the C101. Basically, the x-axis is basically the pressure, and the pressure defined there as the operating pressure plus the transit or the surge, another word to use. So we can do it in two ways. If there's a transit study, we will use the values provided by the transit study. I said the word TPM. TPM refers to transit pressure monitoring. So basically, as a package, and I go here, as a package of adding additional feed measurements, we are using TPM, transit pressure monitoring. In order to, during the inspection, we usually put it for 1 week or 2 weeks to monitor if there's transit event. And if there's a transit event, we monitor the frequency of these transit events. In the absence of transit pressure monitoring, we will use the design standards that recommended in the original design. However, the transit pressure monitoring is not an expensive thing to do. And since we're talking about the distribution mains, there are lots of features that we can install these sensors, and it's an easy thing to do. Hence, we will use, just to boot, the transit pressure monitor is not the pressure loggers that people use. These are advanced sensors that if they detect a difference in 10 psi, they will start sampling in a 20 millisecond data. So you can imagine how much data we will collect to capture the transit. So the way we capture the transit in the condition grading, it's basically implemented in the loads acting on the pipe. When we talk about the internal pressure, it's the operating pressure plus the transit.
Oops. Oh, okay. So we have one more question. Is cathodic protection not a valuable tool as it extends the life of the pipe? And I think you touched on that.
Yes. Cathodic protection stops continuous deterioration of that pipe. However, since we understand now that for order to a failure to occur, it's not only the physical condition, but it's also the applied load acting on it. Therefore, if a client wants to adopt a cathodic protection in their system, they need to do a cost-effective analysis. And the way they will do that cost-effective analysis is they need also to assess the existing stresses acting on the pipe due to imposed loads. It could be from internal pressure, it could be from vertical loads, soil weight, traffic loads, and all these types of loads that we identify. And if we identify that these loads are a huge factor or aspect to lead that pipe to fail, therefore the cathodic protection will become less desirable. If the loads are acting on this pipe are not that significant, it's low pressure, the pipe is not that deep, there's no traffic load acting on this pipe, then, and also there's no aggressive, and there's this, assume there's aggressive environment, then using cathodic protection becomes more valuable. Again, in my opinion, I always see cathodic protection as a temporary solution. for a client that doesn't have the necessary budgets and to build that capital plan, and it can give him that buffer to push decisions to renew. It could be replace or rehab pipes more towards in a later time by using cathodic protection solutions. But it has to be reviewed combined with the loads acting on the pipe.
Okay. Well, thank you very much. Rabia has given us a very informative presentation and lots of very good, um, questions have come in. As we are almost at 1, I'd like to say thanks again to all of our participants, and um, please go to opwa.cpwa.net to find out about future OPWA Connects events. Thanks again, and we'll sign off now.